Hello guys, good morning. Is everything all right? Can you start? So today in this lecture we'll be covering matrix. Is everything all right? Can you start? Okay. So we have covered dimension analysis, then vector analysis, and after that vector lecture I have uploaded two more very important lectures. One lecture on coordinate system, you should watch it, and after that the Dirac delta function. These two lectures you can watch it by yourself, and today we will start matrix. Now this matrix chapter is very easy chapter, but you need to know about something, some properties of matrices and some types of matrices which are very essential for your examination. Okay, now without any further ado, let's start today's session. And guys, try to attend the session live, okay, and in that way if you have any doubt you can clarify it instantly. Okay, let's start with the definition of matrix. So matrix, you already know what is the definition of matrix. So we are starting from a very basic level, so many things you have already known, but still for the sake of completeness we will do them. So first let's go with the definition of matrix. So what is the definition? What is a matrix? Matrix is basically an array of numbers, a square, or it may be rectangular. Array of numbers or functions. So this is a very basic thing, okay. For example, you see 2, 3, 4, 5, it can contain number, it can contain functions, sin theta, cos theta, minus sin theta, cos theta, and anything it can be. Now in matrix there is something called order. I am just defining it one times. So in matrix we have rows are these, the elements which are lying horizontally, okay. So let's say there are m number of rows, right, and these are called columns. So let's say n number of columns are there, and when we talk about the order will be read as m by n, okay. Although this is cross, but it is read as m by n order matrix. The m by n order matrix has m number of rows and n number of columns. Now when we talk about the matrix, the numbers which you write inside, those are called matrix elements. Let's say A11, A12, A21, A22. So let's say this is a matrix. This A11, A12, A21, A22, these are known as matrix element. So you can write it as AIJ, okay. Now for various values of I and j you get the different matrix elements, right. So you already know these things. So this is a 2 by 2 matrix. So you write it in this way, 2 by 2. Now any general matrix, you can express it in this way, A I J M by n. So it represents m by n matrix, okay, and the elements are A I J. By pairing the different values of I and j, we can construct the matrix, right? Now matrix operation, look, is very similar to algebraic operation, few things, but many things are widely different. So let's talk about some of the basic operation. Like in algebraic function, you see, let's say we are adding two numbers, so we don't need to look at the numbers. We can add 1 to 100, anything we can add. But for matrix, the order is important. You cannot add, let's say, a 1 by 3 matrix to some 4 by 2 matrix. So there is some rule or some property which must be valid before we perform those operations, okay? So when we talk about matrix operation, basically 2 or 3 matrix operations are mainly important. Firstly, this matrix addition. Okay, so what is the condition for getting this matrix addition? Addition or subtraction. When you can add or subtract two matrices, so you can just write a line. We can add or subtract two matrices when they have the same order. Okay. Now let's say we have a matrix A whose components are A, B, C, D. Now if we multiply any scalar lambda with the matrix, what does it mean? It means multiplying each element with that scalar. This is a very important property. We will use it many times. Lambda A, lambda B, lambda C, lambda D. Okay. Now let's say this is an identity matrix. Identity matrix. What is identity matrix? For identity matrix, you know, the principal diagonal elements are 1. So if I consider a 2 by 2 identical matrix, it looks like this. Okay. Again, we can consider 3 by 3 identical matrix. Okay. So in a similar manner, let's say I am just writing it I2, I3. If I consider IN, which is a n by n identical matrix, so can you tell me what will be this 2IN? If I consider the magnitude or determinant, what you get? Two IN means what? Look, At each principal diagonal elements 2 will be there. So when you take it outside, it will be 2 to the power n. Okay. Isn't it? Do you understand this? In some of the problems, we are going to utilize this. Tell me, guys, if you have understood this. Let's say we want to multiply two matrices. One matrix is there A, which is having the order m by n. Another matrix we have B, which is having the order p cross q. Now these two matrices, the matrix multiplication will be conformable. Conformable meaning compatible to be multiplied. If n is equals to p. This is a very important thing. So column number should be the row number, then we can find the product. Now what will be the order of AB then? What will be the order of AB? Can you tell me? Order of AB will be m by q, isn't it? So these are some various basic operations you will be doing in matrix, and some more advanced operations are there, functional matrices are there, and which we can discuss in subsequent times. Now let us talk about different types of matrix, which are very important to know. At any point, if you don't understand anything, you can ask me readily. Various types of matrices. So first of all, what is square matrix? In a square matrix, the number of row and number of column will be same. So it will be n by n. Okay, let's say I am just writing Aij. Number of rows will be equals to number of columns. This is square matrix. Second, diagonal matrix. You already know this thing, I am just quickly reviewing. Okay, what is the diagonal element? For diagonal element, only the diagonal elements will remain. Let's say, for an example, this is A1, A2. Other elements are 0. So we can write it in this way. Let's say any matrix, how do we represent? We represent Aij, right? So Aij will be 0 for I not equals to j. You know what are the elements? A11, A22, A33 and so on. Okay. So this is your diagonal matrix. Next, identity or unit matrix. This is already we have defined. Identity or unit matrix. So it is a type of diagonal matrix where the diagonal elements are unity. You know? Here Aij equals to 0 for I not equals to j and equals to 1 for I equals to j. So, this is a way of defining 1 0 0 1, or in 3 dimension you get. Now, this is widely used in quantum mechanics. Row matrix. What do you understand by row matrix? Row matrix are those matrix where you will only have one row, no column, or will have one on row only. The columns are there. Let's say A, B, C. So, in this matrix, how many rows? So, I am just writing having matrix having only one row. So, if you look at this matrix, it has one row, but 1 2 3 columns, 1 by 3, and conversely we can have column matrix. What is a column matrix? As per the name suggests, it will only have a single column. So, it will be written like this: A, B, C. So, how do we write it? How many number of rows? 1 2 3. How many number of columns? 1, 3 by 1. So, we can write it here: matrix having only one column. Understood? Look, these are very simple definitions, but when you will be going to solve problems, these concepts should be very clear. These are fundamental things. Let's move to the next type of matrix, null matrix. What is the meaning of null matrix? Null means zero, void. So, null matrix means here all the elements will be 0. Aij equals to 0 for all I j. For, let's say this is what 1 by 1 matrix, okay, 1 by 1 null matrix. If you have like this is 2 by 2 null matrix, and so on you can construct. Number 7, upper triangular matrix. Upper triangular matrix. Look, triangular matrix means the elements will be there, non-zero elements will be there in the triangular form. Okay, this is the first thing, triangular. Upper means the non-zero elements will be in the upper portion. Okay, so if you have a matrix, let's say this. So if you imagine a line like this, then okay, just hold on. Okay, if you can imagine a line, this line is separating the matrix into two parts. Okay, two triangles actually. If you closely look at, this is one triangle, another triangle below. So upper triangular matrix means only the upper elements will be non-zero, lower elements will be 0. Okay, so let's say A, B, C, these are the diagonal elements, then D, E, F, and all the other elements which are appearing in the lower triangle, they will be 0. So how can you define this in terms of Aij? How can you define this? We can say Aij equals to 0 for all I greater than j. How it is? You see, what is this element? This is A11, this is A22, this is A33, and what is this element? This is A21. You can see I greater than j. This is A31, I greater than j. This is A32, I greater than 0. But if you consider this is what? A13. Here I greater than j. Here I greater than j? No. Here I less than j. In this way, you define upper triangular matrix. I hope you understood. The lower triangular matrix is just the opposite. Lower triangular matrix. So you just need to remember this: triangular and upper and lower, those elements are non-zero. Okay. So the definition will be Aij will be equals to 0. So for these elements, I less than j. So for all I less than j. So if we consider a similar matrix like this, A, B, C, D, E, F. So this is your lower triangle part. But your upper triangle part are all 0. Okay. So this is lower triangular matrix. Let us now talk about periodic matrix. Okay. Number 9, periodic matrix. Now it is similar to periodic function. What you have in periodic function? Any function which repeats itself after some interval. So here for matrix there is nothing like interval, but what you can say, if you multiply the matrix with itself, you get A. Let's say a matrix A is there. If you multiply with itself, you get A square. Then again, if you multiply with A, you get A cube. So if you keep on doing this, and after some time, if you get A back, then you can say the matrix is repeating after some power. So this kind of matrix is called periodic matrix. So how to define this? A square matrix A for which A to the power k plus 1. Let's say if you do A cube and you get back A, then k will be 2. So A will have the period 2. A square matrix A for which A to the power k plus 1 is equals to A is called periodic matrix of period k. Okay. Any example you know for periodic matrix? Identity matrix will be a periodic matrix. If you consider I square, you get back I. So a periodic matrix has a period 1. Or you can take an example. Let's say A is equals to 0, minus 1, plus 1, 0. So if you keep on doing multiplication, a to the power 5, you will get a. So a has a period for you can consider Pauli spin matrices. You know, whenever you take a square of the Pauli spin matrices, you get identity. Then if you take cube, you get back that matrix. So cube means 3, 3 means 2 plus 1, so period will be 2. Now number 10, idempotent matrix. Idempotent matrix is a special case of this periodic matrix. If your k is equals to 1, that is the idempotent matrix. So a square matrix for which a square equals to a is called idempotent matrix. So very straightforward example is the identity matrix, right? Like, or any matrix you can take, any other matrix, 1 1 0 0. If you take a square, you get back this a. So you can say this is a matrix of period 1. Okay, 2 plus 1, so k is equals to 1. Okay, so we have defined the basic types of matrix. Now let us consider some problem. Okay, let's say for the matrix B 0 minus 1 plus 1 0, what is the value of b to the power, let's say 1 0 2 3? Solve this quickly. Simple question. Option A, option B, option C, option D. Do it quickly and tell me the answer. Look guys, let me tell you one thing. Let's say we are taking these classes one after another, we'll be taking and we'll keep on completing each subject. Okay, so you have to allocate some portion of your time, maybe half an hour, for revision. Okay, if you make it a habit of revising the previous notes, then it will be very good for you. Without revision, you will not get all the concepts very strongly. Revision is very necessary. So make it a habit. Fix a particular timing, and in that time you will just do revision, whatever you have read or practiced. If you do it right from the beginning, then it will be very useful for you. Could you find out? Look, whenever this kind of problem will be given to you, your first task would be to find out the square, okay, then cube, then another power, to see if any pattern you can see after doing b square or b cube or b to the power 4, whether you are getting identity. If you get somehow identity matrix, then your job is done. 0 minus 1 plus 1 0. If you take b square, what you get? 0 minus 1 plus 1 0, 0 minus 1 plus 1 0. So this is, you see, minus 1 0 0 minus 1. So it is minus of identity. Now if you take square of this, so minus will be removed. Now you can easily think of finding the value 1023. So we can write it as b to the power 1020 and b cube. 1020 is divisible by 4. So we can write b to the power 4 times 255, and what is the value of b cube? B square is equals to minus I. So b cube will be minus b, right? So I times this is minus b. So minus b means each element should be multiplied by minus 1. So this is 0 plus 1 minus 1 0. That is matching with option B. Let us now talk about trace of a matrix. What is trace? Anyone knows? Trace of a matrix. Can you define it in words? Trace is nothing but the sum of the principal diagonal elements. One thing I would like to highlight here, look, in matrix you can see there are two diagonals. One is this is one diagonal, this is another diagonal, but principal diagonal is this diagonal. This diagonal is the principal diagonal, not this. Okay, just know this. So elements on this line is known as the principal diagonal elements, and the other elements are known as off diagonal elements. This is just some nomenclature. So if you have a matrix, let's say A, so trace will be the sum of the principal diagonal elements A11, A22, A33, and it can be valid for ANN, for n by n matrix. So you can just write it in the summation form, I is equals to 1 to n A I I. Okay. Now this trace has very important properties and questions are framed from this based on these properties. So if you calculate the trace of addition of two matrices, so you can write them as individual sum of individual traces, trace of A plus trace of B. Now if you calculate the trace of a matrix where a scalar is multiplied, we can take out the scalar in this way. Now a trace of product of two matrices, let's say AB, will be same as trace of the product of this reverse matrix BA. Now the fourth one is very important. Trace of, let's say, four matrices are there, A, B, C, D. You can just rotate it in cycle. It is like you are just moving one position. Trace of A, B, C, D. So you can just write B, C, D and A will come at last. B, C, D, A. Many questions framed from based on these properties. Now you see B has come now here, we can write C, D, A and this B will go at the end. Trace of C, D, A and this B will come at the end. Again you can form, now you see D, A, B and this C will come at the last. Trace of D, A, B, C and you will get back eventually trace of A, B, C, D. Okay. So these properties are very important properties regarding the trace of a matrix. Now what do you understand by transpose of a matrix? Transpose of a matrix. Transpose of a matrix is constructed by interchanging the row and columns of a matrix. It is formed by interchanging the rows and the columns of a matrix. Okay, let's say I am considering a matrix like this, 1, 2, 3, 4, 5, 6. So what will be A transpose? A transpose means the elements will be now written in this way: 1, 4, 2, 5, 3, 6. So previously it was 2 by 3, here it will be 3 by 2. Now this transpose also has some properties. Okay, hold on a moment, be back. Now what are the properties of transpose of a matrix? Okay, let's talk about the properties of transpose of a matrix. If you take the transpose of the transposed matrix, you get the original matrix. Obviously, if you take transpose again, then you will again get back 1, 2, 3, 4, 5, 6. Now the second property is important. Let's say we have a product of two matrices. Look, it will always be operated from the right. It will not be A transpose B transpose. It will be B transpose A transpose, and we will see it later. For inverse also it will work. A B whole inverse will be B inverse A inverse, not A inverse B inverse. Remember this thing. A similar concept is there. Transpose conjugate. What is transpose conjugate? Transpose conjugate of a matrix. Transpose of a matrix means writing the rows along the column and columns along the rows. Transpose conjugate means you have to take the complex conjugate. Okay, so you can consider it in this way. I'm just writing it in this way. Transpose conjugate, you can write it like you have to take transpose plus complex conjugate. Complex conjugate means wherever you see I, it will be replaced by minus I. This is a simple meaning of conjugate. So conjugate matrix, transpose conjugate is written as a dagger. This symbol is called dagger. So you have to first take transpose, then you can take complex conjugate, or you can first take complex conjugate and take the transpose. This order doesn't matter. You can take transpose, then complex conjugate, or complex conjugate and transpose. Let's say for an example, I'm giving you a matrix. Let's say A 0 plus I, 2 minus I, 3. This is a matrix. So A transpose will be 0, 2 minus I plus I, 3. A transpose conjugate will be 0, 2 plus I minus I, 3. This will be your A dagger. Now the properties are similar. Properties of transpose conjugate. If you take the dagger of a daggered matrix, you get back the original matrix. And again, A B dagger, if you take, you get B dagger, A dagger. Clear? You guys are attending the class like silent observer. Say something, right? And it will be more interacting. Let's go for two very important concepts: symmetric matrix and skew symmetric matrix. Okay, chalo. Skew symmetric matrix and symmetric matrix. Firstly, let's talk about symmetric matrix. Look, the name basically gives you an idea. Symmetric. For symmetric matrix, A transpose equals to A. If in terms of the matrix elements, you can consider like Aij is equals to Aji. Means if you consider A12, let's say A21 will be same. A13, let's say A31 will be same. A21 and A12 will be same. Okay. For an example, look, if this is A11, A22, A33, so these elements will be unique. Now when you consider this element, let's say B, it is what? A12, so it is equals to A21, so B will come here. Here it, if you let's say consider C, what is this? A13, so A31 will be same. Let's say this is D, what is this element? 2 3, so 3 2 means this element will be same. You don't have any doubt? Okay, Mulyadharan. These topics are very simple, so there should not be any doubt, but still you should say something, okay? At least I can understand that you are getting, otherwise how will I understand whether you are understanding or not? Chalo, 1 8 5, okay? So if I write 2 here, 2 should be written here. If I write let's say 6 here, 6 should be written here. If I write 4 here, 4 should be written here. So you can see a correspondence: 2 2, 6 6, 4 4. So what you can see, all the elements are not unique or independent, they are dependent. So can you tell me how many independent components are there? 1 8 5, these are 3 independent components, and 2 6 4, so total how many? 3 4 5 6 elements, no? They are independent. So there is a formula to calculate this: the number of independent components of n by n symmetric matrix is, you have to remember this formula, half times n into n plus 1. And here we counted 6 because this is a 3 by 3 matrix. This is half times 3 into 3 plus 1. So this is 3 into 2, 6 as expected. 6 elements. Which are those 6 elements? Let me tell you: 1, 2, 3. And for 2 we will only consider 1 independent. 4, 5, 6. Understood? Let's go for skew-symmetric. If you have understood symmetric, then understanding skew-symmetric is very easy. Skew-symmetric matrix. Look, the problem happens when we individually learn about this matrix, then we find it extremely easy. But when we will be doing some problem where you will be given 4 options, you will be given a matrix and will be asked what kind of matrix is this. It is symmetric, schizo-symmetric, Hermitian, anti-Hermitian, unitary, orthogonal, different types of matrices options will be given. At that time you will get confused. Okay, now so if you don't practice enough, you will make mistake. These are you will make mistake because these are extremely simple. So there is a chance of like intermingling between them. Okay, for square-symmetric matrix, A transpose equals to minus A. In terms of the matrix elements, Aij will be equals to minus Aji. Now this condition gives you a special finding. Now Aij equals to minus Aji. If you consider the principal diagonal elements are denoted by Aii. So if Aii is equals to minus of Aii, from this you get 2 Aii equals to 0 and Aii equals to 0. What does it mean? It means the principal diagonal elements of a square-symmetric matrix will always be 0. This is very interesting thing. So you can take an example. As we have obtained from this, all the principal diagonal elements will be 0 and Aij equals to minus Aji. So if I write B, here it will be minus B. If I write C, here it will be minus C. If I write D, this is 2, 3, so 3, 2 will be minus D. Got it? Now here, what is the formula for the number of independent components of n by n? Schizo-symmetric is also called antisymmetric. Antisymmetric matrix is half times n into n minus 1. Only a minus sign will be there. For symmetric it is half into n into n plus 1. Here it is half times n into n minus 1. This is the first note. The second note is this, which we have already written. The principal diagonal elements are 0. So note number 2 you can write. The principal diagonal elements are all 0 here. Now few other interesting things are there. If you have, let's say, a square matrix, so you can write the square matrix as a sum of symmetric matrix and antisymmetric matrix. Let me tell you how it is. Any square matrix can be written as the sum of symmetric and antisymmetric matrix, right? Just write it down. And look, these properties we will be utilizing in solving various problems later on. So every square matrix can be written as the sum of symmetric and antisymmetric matrix. And this property also holds for tensors. Any tensor we will see can be written as sum of symmetric and antisymmetric tensors. So if you have a square matrix, let's say A, it can be written as, look, half, just to make it equal to A, half, there is nothing significance of half here other than making with balance between the left hand side and the right hand side, half into A plus A transpose. This A plus A transpose, this is itself a symmetric matrix, okay. And half A minus A transpose, this A minus A transpose is the antisymmetric or skew symmetric, this half factor just to make it equal to A. So let me tell you, here this A plus A transpose, this is your symmetric matrix, and this part is the antisymmetric or skew symmetric. Okay. Now look at these statements. If you understand, then you don't need to remember. If A and B are symmetric matrices, then AB will be symmetric if and only if A and B commute. Do you understand the last line? If A, B are symmetric matrices, then AB will be symmetric if and only if AB commute. You can do some little bit of calculation. AB will be symmetric means AB transpose should be equals to AB. At what condition? If A and B commute. A and B commute, it means this equals to 0, AB minus BA equals to 0, AB equals to BA. Now let's see how this is hold. AB transpose, I have already told you, it is operated from the right. This is B transpose, A transpose. Now if A and B are symmetric matrices, means B transpose will be B, A transpose will be A. Now if A and B commute, we see AB is equals to BA, so BA is equals to AB. Hence proved. You see, this is a proof actually. Okay, let's move towards a more important matrix, Hermitian matrix. What is Hermitian matrix? Look, we discussed about transpose and transpose conjugate. Corresponding to transpose, we have symmetric, antisymmetric. Corresponding to transpose conjugate, we get Hermitian, skew Hermitian. Okay, remember this simple fact. Okay, whether you have defined transpose, for transpose we get two types, symmetric, skew symmetric. Then we defined transpose conjugate by dagger. For this you will get Hermitian and anti-Hermitian. And similar, the way you define symmetric, you will define Hermitian. The way you define skew symmetric, you will define anti-Hermitian. So Hermitian will be matrix for which A dagger will be equals to A. If you talk about In terms of the matrix elements, it is Aij equals to Aj. Look, this was the case when we consider symmetric, but here it is conjugate, so star will be there. So Aij equals to Aj star. So if you take an example, principal diagonal elements A, B, C. Now off diagonal elements A, 2, 1. If I consider, let's say D here, A12, this is A12, A12 is D, A21 will be D star. If you consider E, this will be E star. If you consider F, this will be F star. This is the basic difference between symmetric and Hermitian. यहाँ पे A, B, C all belongs to the real numbers, and this is a very important part. The diagonal elements are real for Hermitian matrix, principal diagonal elements. Principal diagonal elements of Hermitian matrix are always real, and this property is very much useful. You must have seen in quantum mechanical operator also, it is always taken Hermitian operator because the eigenvalues are real. Now what is the minimum number of real elements? Can you tell me minimum number of real elements for the most general n by n Hermitian matrix? Can you tell me what is the minimum number of real elements in an n by n Hermitian matrix? Can you tell me? मिनिमम कितना हो सकता है? Think about it. Let's now talk about skew Hermitian. Skew Hermitian matrix is equivalent to the skew symmetric matrix. A matrix for which A dagger is equals to minus A. देखो Aij equals to minus Aj star. Okay. Now here we cannot say that the principal diagonal elements will be 0. It may be 0 or it may be imaginary. Okay na? Because if it were real, then we could take this elements on the right to the left, and as a result we got it to be 0. But because of this star, we cannot say that it will be 0. It may be 0 or purely imaginary. This is what we can say. If you construct this skew Hermitian matrix, let's say A, B, C, Aij equals to minus Aj. So if I write D, it will be minus D star. If I write, let's say, E, it will be minus E star. If I write F, it will be minus F star. Okay, A, B, C can either be 0 or purely imaginary. Okay, so what is the answer of this? Minimum number of real elements? Deep N. Yes, because only the principal diagonal elements are the real elements. And how many principal diagonal elements? The order n by n, so it is n. Okay, so you can just write it as a note. The first point is this principal diagonal elements can be either 0 or purely imaginary. The principal diagonal elements of a square Hermitian matrix are either 0 or purely imaginary. And what is the minimum number of real elements? Can you tell me? The minimum number of real elements in the square Hermitian matrix. Anyone? Just think little bit and tell me what should be the minimum number of real elements in a most general n by n square Hermitian matrix H. Just think about the first line, first point, and tell me what is the minimum number of real elements in a most general n by n square Hermitian matrix. 0. How it is 0? In under what condition it will be 0? You see, ABC can be either 0 or purely imaginary. If all the elements are imaginary, I, let's say, then what is the minimum? What is the number of real elements? 0. Okay. Now, few more properties. If let's say A is Hermitian matrix, if A is Hermitian matrix, A is a Hermitian matrix, then IA and minus IA, both of them will be anti-Hermitian or skew Hermitian. If you multiply some scalar with the Hermitian matrix, will it remain Hermitian or will it become skew Hermitian? What I am trying to say, let's say you have a matrix, let's say A. Then if I multiply a scalar k with the matrix, will it remain Hermitian or not? Ka will also be a Hermitian matrix. But if you multiply this imaginary number, then it will become anti-Hermitian. If you multiply real number, then there is no problem. It will remain as it is. Okay, let us now solve a few problems. Now you are in a position to tackle problems. Theory part we have covered almost, few parts are remaining still. Okay, too much gap. Can you solve this? The number of independent components of a general electromagnetic field tensor. देखो, if you do not know about electromagnetic field tensor, we will be discussing this electromagnetic field tensor when we will be covering the special theory of relativity, but for the time being I am just giving you electromagnetic field tensor is represented by F mu nu. This is a tensor. Okay, F mu nu is equals to minus of F nu mu. So electromagnetic field tensor, it is anti-symmetric. Okay, now the components of F mu nu, just write it for the timing. We will be discussing about it more when we will be covering this. 0 0 0, this is a 4 by 4 matrix. Okay, this element is 0 0 0 1 0 2 0 3. Okay, this is 1 0 1 1 1 2 1 3. In this way you will consider. In a 3 by 3 matrix we used to consider A11, A12, A13. For this 4 by 4 you will consider from 0 0 0, this is 1 1 2 2 3 3. So F01, it means this component, sorry, this component is 0 0 0 1. If I talk about F02, this means it is talking about this component. F03, it is talking about this. So F01 is Ex by C, 02 Ey by C, 03 Ez by C. Ex, Ey, Ez are the components of electric field, right? Ex by C, Ey by C, Ez by C. Now you get the antisymmetric properties. So F01, so F10 will be how much? F10 will be minus Ex by C, F20 will be minus Ey by C, F30 will be minus Ez by C. So this is 10, so minus Ex by C, this is 20 minus Ey by C, this is 30 minus Ez by C. Now we have to consider, this is a way of remembering these things, 1 2 3, let's say. So F12 we will take first. F12 means which element? This element. This is Bz, right? F12 we have considered, then we will go for F31. 1 2 we have taken, then 3 1. F31, this will be Bz, it will reduce by 1 unit, Bz to Bi. 3 1 done. Then what is the next? 1 2. Okay, 3 1 is done. So next is 2 3. Firstly we took 1 2, secondly 3 1, thirdly 2 3. So Bz, By, what is expected? Bx. 1 2 means this, Bz, 3 1, 3 0 3 1, By, 2 3, 2 0 2 0 2 1 2 2 2 3. So this is Bx, and from the antisymmetry property we can find out F21, minus Bz F13 minus By and F23, so 32 minus Bx. So this is what point? This is 13, so it will be minus By. This is 32 or this is 21 actually, minus Bz. This is 32 minus Bx. So this is your electromagnetic field tensor. Now can you solve this problem? Number of independent components of a general electromagnetic field tensor. I have already given you the formula. Okay, I have also specified the tensor. Now what is the answer? A, B, C, D. Out of this, what is the answer? Tell me. I think you can do it in seconds. It is a 4x4 matrix. C, 6Ri. So let's calculate. This is this electromagnetic field tensor. This is a squishymetric. Squishymetric matrix. So the number of independent components half into n minus 1, half into 4 minus 1. So this is 6. ठीक है, चलो. So let's move on to the next question. The product Mn of two Hermitian matrices plural form M and N is anti-Hermitian. It follows that look, this symbol is denoting anti-Hermitian, Mn, anti-commutator. This is commutator. Third bracket commutator, second bracket anti-commutator. Until and unless it is specified in the question, this is the normal system. बताओ which one of this is correct? The A you are getting. Okay. M N are Hermitians. So M dagger equals to M and N dagger equals to N. These are the given conditions. And Mn dagger equals to minus Mn. This is also given, na? So let's take up this Mn dagger equals to minus Mn. Right hand side you can write N dagger, M dagger equals to minus Mn. Now N dagger is equals to N, M dagger equals to N, and this Mn equals to 0. Order doesn't matter for addition. So Mn plus Nm equals to 0. Plus means anti-commutator. So option A, obviously. Okay, let's quickly move on to the next problem. For any operator A, I times A dagger minus A each. Do this quickly. Hermitian. Okay, let's do this. A times A dagger minus A. To check Hermitian, what we have to do? We have to take dagger. Okay, look, taking dagger, so I will be minus I, right? A dagger and dagger, it is A, and this is A dagger. Okay, A dagger is A, and A dagger, this is equals to, if you consider I, then negative sign is taken inside A dagger minus A. So we are getting back, this is a property of Hermitian matrix, that is I times A dagger minus A is a Hermitian matrix. Chalo. Now 2-3 small things are there. Let's talk about it. One term you will see while finding the inverse of a matrix, singular matrix. What is singular matrix? Matrix having zero determinant. Okay. Non-singular. Matrix having non-zero determinant. Okay. Now, while finding inverse, we will be requiring adjoint. Adjoint of a matrix. How to calculate the adjoint? Adjoint is found by considering or finding cofactor of a matrix. So it is defined as the transpose of cofactor matrix. Now finding this cofactor, you need to know, let's say if you have a matrix whose matrix elements are A11, A12, A13, A21, A22, A23, A31, 32, 33, then adjoint of A, you see, you have to take transpose of the cofactor matrix. Like A11, if its cofactor is, let's say, C11, A12, its cofactor is C12, but it will not be here, it will be here because we have taken transpose. A13, the cofactor is, let's say, C13, but it will not be here, it will be here. Okay. Similarly, A21, C21, A22, C22, A23, AC23. You are reading along row direction, but you are writing along column because of the transpose. C31, C means cofactor, C32, C33. This is the adjoint of matrix A. Example, let's say 2 by 2 matrix. How do you find out the cofactor? Let's say you want to find out the cofactor for A11. What do? You remove this row and column and you consider this, the determinant of this. Okay, but symbol for each cofactor will be different. Like A11, the symbol will be minus 1 to the power 1 plus 1. A12 cofactor will be found by removing this column, this row. So A21, A23, A31, A33. This will be the determinant. But a symbol will be minus 1 to the power 1 plus 2. So negative of that thing. A13, when you calculate, then you remove this. So this will be used in finding the cofactor. So A13, minus 1 to the power 1 plus 3. So that is positive. Giving you an example. Let's say 1, 2, 3, 4. This is the matrix A. So cofactor you find, cofactor of A. Cofactor of A will be, look, adjoint, for adjoint it will be transpose, but for cofactor there is no transpose. So for 1, what is the element? If you remove this and this, it is 4. Okay, this is A11, minus 1 to the power 1 plus 1, so positive. So this will be 4. For 2, this is 1, 2. So minus 1 to the power 1 plus 2 is negative, and so negative of 3 will be there. Okay. For 3, this is 2, 1. This is also negative, so negative of 2 will be there. For 4, just remove 1, so it is positive 1. Adjoint of A will be the transpose of this cofactor matrix of 4 minus 2 minus 3 plus 1. Okay. Let's talk about the properties of adjoint of a matrix. First of all, adjoint of A times the matrix A equals to A times adjoint of A. This will be determinant of A times n by n identity matrix. Second, if A is a square matrix of order n, having determinant, let's say m, then modulus of adjoint of A will be m to the power n minus 1. Okay. Now once we get the idea of adjoint, we can find out the inverse of a matrix. Let A be a square matrix of order n and B be a square matrix of order n such that AB is equals to BA equals to IN. IN is the identity matrix of order n. Then this B is equals to A inverse of matrix A, and it is defined by adjoint of A divided by modulus of A. Now you see, if this modulus of A means the determinant of A becomes 0, then it will be undefined. That is why for the inverse to exist, the matrix should be non-singular, having non-zero determinant. A is then called invertible matrix. So you cannot find inverse of all the matrix. It should be non-singular to get an inverse. Now few important properties we can consider for this inverse of a matrix. Any invertible matrix possesses an unique inverse, means there will be no multiple inverse, only one inverse will exist. The necessary and sufficient condition for a square matrix A to possess an inverse is that it is non-singular. And the third property is similar. Let's say if you have product of matrices and if you take the inverse, then the inverse operates from the right. Okay, C inverse, B inverse, A inverse. Let's go for a problem. If I is an identity matrix of order n by n, then adjoint of 2i is equals to 2 to the power k times I. Then k is equal to 1, 2, n minus 1 or n. Can you solve this? Look, A is given to be an identity matrix of order n by 1. You have to find out adjoint of 2i. So let's forget about it. First, what is A inverse? Because why you are taking this? Because adjoint appears in inverse. So adjoint of A divided by modulus of A, right? So if we multiply with matrix A, what you gonna have? A in A inverse will be identity, right? So A times I. A inverse equals to identity. Using this property you can write it. Now here adjoint of 2i, so it is like it is talking about the matrix 2i. So the A is in a general matrix, so in place of A we will write 2i. This is the matrix we need to handle. A is 2i, modulus of 2i multiplied by I. So what is the modulus of 2i? अच्छा, यहाँ पे मॉडुलस की बात हो रहा था, तो हम लोगों ने पिछले जगह पे हम लोगों ने वी हैव डन दिस ना 2 to the power n with yes, देखो 2 to the power n modulus of identity matrix is 1, so this is 2 to the power n, right? This thing now we will be utilizing. Okay, look at this now. 2 times identity matrix is 2, adjoint of 2i. 2i modulus means 2 to the power n, because n a matrix is there where each element principal diagonal elements 2, 2, 2, 2 and so on, and all other elements are 0. If this is a matrix, so to make it an identity matrix we have to take common. 2 will come from here, 2 will come from here, so n number of 2's will come. So 2 into 2 into 2 into 2 is 2 to the power n, so that is why 2 to the power n. Here adjoint of 2i, this is 2 to the power n minus 1 time I, it is 2 to the power k. So from this we can say k is nothing but n minus 1. Now two very important matrices are left. orthogonal matrix and unitary matrix, and after that I think everything will be over. Let's talk about, you have already learned in vector, but for matrix this is a little different. Orthogonal matrix, give the heading orthogonal matrix. What is an orthogonal matrix? A square matrix is said to be orthogonal if A transpose equals to A transpose A equals to I. For unitary, transpose will be replaced by dagger. Okay, A transpose equals to A transpose A equals to I. Let's write some note. Determinant. What is the determinant of an orthogonal? Determinant of an orthogonal matrix will either be +1 or -1. Remember this thing. Number 2, A transpose is equals to I by A, so A transpose equals to I inverse. Another thing, each row and column of an orthogonal matrix is a normalized vector. Do you understand the meaning of this? Let's say an example of orthogonal matrix. Orthogonal matrix example हम लोग यहाँ पे लिखते हैं. Example is, let's say A, it is cos theta sin theta minus sin theta and cos theta. This is the orthogonal matrix. A transpose, you take A transpose, this will be cos theta minus sin theta cos theta. This will be equals to A inverse. Each row and column of an orthogonal matrix is a normalized vector. So if you consider this row, let's say this row, cos theta sin theta is there, right? So cos square theta plus sin square theta is 1. If you consider this column, cos theta minus sin theta, cos square theta minus of sin theta whole square, that is again 1. So each row and column of an orthogonal matrix is a normalized vector. Either you consider cos theta sin theta, so root over of cos square theta plus sin square theta, that is 1, so normalized. Or you can take any column vector, cos theta minus sin theta, again cos square theta minus sin square theta, that is 1. Okay. The fourth property, any two rows or any two columns of an orthogonal matrix are orthogonal to each other. Isn't it? For an example, any two rows or any two columns. Two rows, we can take one row, let's say cos theta, sin theta. This is one row, let's say let's name this x, and another row is minus sin theta, cos theta. So any two rows or any two columns of an orthogonal matrix are orthogonal to each other. So if you calculate x y transpose, what you get? Or if you consider x transpose y, are you getting? Are they orthogonal? So any two rows or any two column will be orthogonal to each other. If you consider this form, you will get identity. Chalo. This is the fourth property. Fifth property, A and B, if they are both orthogonal, then AB will also be orthogonal. If A and B are orthogonal matrices, then AB and BA will always be orthogonal. Now unitary, in unitary instead of transpose we will consider dagger. Let's define unitary matrix. Unitary matrix. So a square matrix is said to be unitary if a dagger equals to a dagger A equals to identity. So transpose has been replaced by dagger and other things are remaining same. Now some important properties of unitary matrix is there. Determinant, if you consider determinant of an unitary matrix, for the orthogonal matrix determinant you have seen it is either +1 or -1. So here as you can see, determinant of A is +1. Determinant of unitary matrix will be of unit modulus. Unity, why did we not say unity? We are saying unit modulus because complex thing will be there. Okay, unit modulus means let's say if you have 1, that is a unit modulus. If you have I, then again modulus of I is 1, isn't it? I is 0 plus 1 times I. So modulus of I, 0 square plus 1 square, 1. Okay, that is why the name unit modulus. Again, A dagger A is equals to I, so A dagger is A inverse. So you just find out the dagger, you can find out the inverse. If you know that it is a unitary matrix, you can write dagger to be its inverse. Third, each row and column of an unitary matrix is a normalized vector. Same as before, normalized vector I have already shown you, not saying it now. Any two rows or columns of an unitary matrix are orthogonal to each other. Number 5, if A and B are unitary matrices, although the properties are very similar, then AB and BA will be unitary. Okay. If I take an example, let's say we have a matrix like this: A 1 upon root 2, 1 upon root 2, 0, minus I upon root 2 plus I upon root 2, 0, 0, 0, 1. Let's check whether it is an unitary matrix or not. So what you have to find out? You have to find out A dagger. A dagger means transpose and complex conjugate. So we'll read column wise but write row wise. 1 by root 2 minus I by root 2 complex conjugate we have to take also. So I by root 2, 0, 1 by root 2 minus I by root 2, 0, okay, 0, 0, 1. Now A dagger you calculate. If you calculate A dagger 1 by root 2, so 1 by 2, so this is 1, okay, 0, 0, 0, 1, 0, 0, 0, 1. This is identity. Let's go for some problem. We have a lot of problems. Okay, now this is a kind of problem I was talking about previously. You will be given a matrix and you will be asked whether it is orthogonal, symmetric, antisymmetric or unitary. So find it out. A matrix is given to you. You have to say whether it is orthogonal, symmetric, antisymmetric and unitary. Can you do it? Look, first of all, imaginary numbers are involved, so you should check for unitary. Orthogonal A transpose you can check if it's satisfied. Symmetric, right? If you consider, let's say A transpose 1 by root 3, 1 minus I, 1 plus I minus 1. So obviously this is not symmetric and antisymmetric, nothing. So these two options are not working. Let's consider A dagger. A dagger is A transpose star. So it is like 1 upon root 3, 1 plus I, 1 minus I minus 1. Okay, so let's calculate A dagger. So 1 by root 3 into 1 by root 3, 1 by 3. A is 1 minus I, 1 plus I minus 1. A dagger is 1 plus I, 1 minus I minus 1. Okay, 1/3, 1 plus 2, 3, 0, 0, 3. 1/3, 1, 0, 0, 1. This is nothing but an identity matrix. So A is an unitary matrix. Unitary, A और N क्या होगा? यस दीप, ऑप्शन डी. ए यूनिटरी होता है या एन यूनिटरी? ए यूनिटरी और एन यूनिटरी. ए यूनिवर्सिटी और एन यूनिवर्सिटी. These things are confusing, guys. According to me, it should be a unitary matrix. Tell me, A or N? Let's check your English. Chalo, this will be a unitary matrix. Okay, let's move on to the next question. Came in December 2012. Now look, the theory part is you have understood. Now you can solve any problem. Given a 2 by 2 unitary matrix, देखो यहाँ पे U देखकर ना, 2 by 2 unitary matrix U satisfying U dagger U is equals to U dagger equals to 1 with determinant of U is equals to the power 5. One can construct a unitary matrix V with determinant V equals to 1 from it by this one. You have done it repetitively. Tell me the answer. Yes, Muralidharan. Which one is correct? U given to be unitary. Now if you want to make a V to be unitary, which is constructed from U, what should be the multiplication factor to U? U is a matrix, 2 by 2 matrix. Let's say an arbitrary matrix setting A, B, C, D. So determinant of U will be AD minus BC, and this determinant is given to be e to the power I5. So AD minus BC is e to the power I5. This is given to you. One can construct matrix B such that determinant of B should be 1. So multiplying u by e to the power minus I phi by 2. So let's check the first option. Let v is equals to e to the power minus I phi by 2 times u. So v, if you want to multiply, say scalar, right? E to the power minus I phi by 2, this is a scalar. So it will be multiplied with each element. So e to the power minus I phi by 2, it is getting multiplied with each element. Okay. If you calculate the determinant, what you get? If we get determinant of v equals to 1, then this is the correct answer. So let's calculate determinant of v. So this e to the power minus I phi by 2 into the power minus I phi by 2, so e to the power minus I phi AD minus e to the power minus I phi BC. Now AD minus BC we have already seen e to the power I phi. So e to the power minus I phi times e to the power plus I phi. This is identity 1. So this is what it is asked. Determinant v should be 1. So by taking this, by multiplying u by e to the power minus I phi by 2, we are getting determinant of v equals to 1. So that is the answer. Option A. Have you got it? This question came in December 2012. Now let's take a problem which came in June 2022. चलिए, this problem came in June 2022. Two n by n invertible real matrices A and B satisfy the relation AB transpose equals to minus A inverse B whole inverse. If B is orthogonal, then A must be lower triangular, orthogonal, symmetric, antisymmetric. Look, each and every matrix given in the option we have already discussed separately. बताइए, what about the answer for this question? Let me know in the comment section. Look, are you able to do it? Muladhar, Deep, Dep. B is orthogonal, then A must be. B is orthogonal. That is B transpose equals to identity. You can write it. देखो A B transpose is given to be minus A inverse B whole inverse. This is given. So we can say that B transpose A transpose, you know, it acts from the right. So B transpose A transpose D array antisymmetric. Let's check. This is equals to minus, you see, B inverse, A inverse inverse, so A. So B transpose is what? B inverse. Okay. So B transpose equals to B inverse A transpose equals to minus B inverse A. So B inverse is getting cancelled. So A transpose equals to minus A. And this is a condition of antisymmetric. ठीक है. Let's move on to the next problem. Yeah, this is a special problem. I'm giving it as homework. The matrix A is equals to this is a unitary matrix if, take this as homework, you can share it in the group, WhatsApp group which you have made. After solving, you will share it in the WhatsApp group. Let's say this is homework. Okay, this is the one homework you get. One last concept we'll discuss, then we'll wrap up the session. Okay, and you will try this problem at home. Another thing is left, that is rank of a matrix. Do you know what is rank of a matrix? Any idea? Anyone? What do you understand by rank of a matrix? In previous year questions came, that is why we are covering this part. Rank of a matrix. Rank, we can define it in this way: the smallest submatrix having non-zero determinant. The order of the smallest square submatrix having non-zero determinant. देखो, a natural number R is said to be, natural number means it cannot be fraction, it will be 1, 2, 3, 4 in this way. Natural number R is said to be the rank of the matrix A if it has the following properties. What are those properties? Number 1, there exists at least one square submatrix. Submatrix means matrix, smaller matrix formed from the bigger matrix. One square submatrix of the matrix A of order R having non-zero determinant. Okay. Number 2, every square matrix, submatrix of A of order more than R, R plus 1, have zero determinant. Okay. So if you summarize this whole thing, you just need to remember this line. which I have told in the beginning. Rank of a matrix equals to order of the largest square submatrix of the given matrix having non-zero determinant. Okay. Now some important note about this rank of a matrix. If you have a null matrix, so what is the rank of a null matrix? There is no submatrix having non-zero determinant. Null of a matrix is, rank of the null matrix is 0. Okay, and any matrix which has non-zero elements, the rank of any non-zero matrix is greater or equals to 1, right? If there is only one element, then the rank will be 1. More than one element, 2 by 2 it can be, the rank will be 2. So at least it will be 1. Now if any matrix is non-singular in itself, so what will be the rank? The rank of any non-singular matrix of order n is n. If you get non-zero determinant for the matrix itself, that is the largest largest submatrix, square submatrix which have non-zero determinant. So that will be the order will be the rank. Now what about the rank if we take product of two matrices? The rank of a product of any two matrices cannot exceed the rank of either matrix. Let's say if you are multiplying two matrices, one of them have rank 2, another one let's say have 2, so the product cannot have more than 2 rank. So I hope you have understood about the rank. Let's take some example so that you understand it better. Let's say a matrix is there A, 3, 2, minus 1, 0, 3, 4, 5, 1, 2. This is a matrix. Now how to proceed to check what is the rank? First of all, you will check the determinant of this matrix, right? So determinant of this matrix, if you get it non-vanishing, then that will be the order will be the rank. So 3 times 6 minus 4 minus 2 times 20. Okay. Minus 1 times minus 15. So this is not equals to 0. So rank of A is 3 because you have found the largest non-vanishing subsquare matrix. Another example, let's say another matrix is there, 2, 1, minus 1, 0, 3, minus 2, 2, 4, minus 3. Let us now check. If you consider the determinant of B, what you get? 2 times minus 9 minus plus 8, okay, minus 1 times zero plus 4 minus 1 times 0 minus 6. Minus 20, yes, minus 2 I have already taken, so 0 also minus 20, ठीक, चलो, this will be equals to how much? Minus 2 minus 4 plus 6, 0. So we can say that rank of B cannot be 3. Let's take any smaller subsquare matrices. So you can take any of them. You can take this submatrix 2 1 0 3. You can take this. You can take this. You can take this. If you take any 2 by 2 submatrix of B, let's say we are taking this 2 1 0 3, this is 6 minus 0, so 6, so we can, this is not equals to 0, so you can say that rank of B is equals to 2 because the order here is 2. Understood? Rank. Look, whenever you will solve problems in CSIR-NET, you will not get the answer if you go every time in a straightforward way. You can use several techniques. Many techniques I have already talked about. You can go for dimension analysis technique, you can take value putting technique, you can go for elimination technique, option elimination technique. Several techniques are there. Don't think that you have to do it in the regular way every time, because sometimes doing the solution in the regular way may be very time consuming. So in that case, you can take any standard example and you can check the options and you can get the right answer. So you have to do some smart work during examination. Okay, so always keep your eyes open. One problem came in December 2019 regarding this rank. So look at this problem. If the rank of an n by n matrix of A is M, where m and n are positive integers with 1 less than m less than n, the rank of the matrix A square. One thing we have told you that the rank of a matrix cannot exceed, the rank of a product of any two matrices cannot exceed the rank of either matrix. So obviously if the rank of this matrix A is m, it will not exceed, means 2m cannot be the option. This option we can eliminate. Now it can be m minus 1 or m minus 2. Now you have to select. Can you do this? This is the last problem for today. For that we will wrap up the session. Can you do this? If you remember, for the Pauli spin matrices, square of the Pauli spin matrices is identity. Pauli spin matrices, they are itself non-singular, and when you take a square of them, What do you get? Identity matrix. Identity matrix is also non-singular. Pauli spin matrices are non-singular in itself. Squaring Pauli spin matrices gives you identity matrix, which is also non-singular. So, does the rank change? No. I am taking an example. A is any matrix, so it will be applicable to any matrix. Okay. Sigma X is a Pauli spin matrix. What is the value? What is the matrix? 0, 1, 1, 0. Okay, na? So this is a 2 by 2 matrix. So rank is 2. Sorry, order is 2. Rank is m. So what is the rank? This is a non-zero. Determinant of sigma x is non-zero. So m is 2. 1 less equals to m, less equals to n. Let's check. 1 less equals to m is 2, less equals to n 2. So this criteria is satisfying. So we can take this example. Now the rank of the matrix A square. So let's say this A is sigma x, A square is sigma x square. So it will be obviously identity. We know it, 1 0 0 1. This is again 2 by 2 matrix. Here order is 2, rank is also 2. So previously the rank was 2, here also rank is 2. So rank of matrix A square is m. So sometimes we need to take some example based approach. If you know any standard result, you can plug in it in verifying the options. You can check it in verifying the options and you can get the correct option. Understood this one? Chalo फिर let's wrap up the session here and we'll see you guys tomorrow at the same timing of 8 AM. The link will be given in the WhatsApp group. And guys, those who are watching, if you have not enrolled for this course, you can also enroll for this course. The link is given in the description. Okay, you can call me on this number for any doubts, query, and the homework problems which I am giving, you can share it on the group. The recording will be uploaded in the course folder, you can get. And let me tell you, the next lectures we have already uploaded. This is lecture 8, matrix part 1. Lecture 9 has been already uploaded, matrix part 2 has been already uploaded. You should watch it by today, okay, so that we can go for lecture 10 on the next day. Lecture 10 will be the third part of matrix. The second part of matrix has been already uploaded, you should watch it. Chalo, with this note, let's end the session here today. Bye bye, take care. If you are new to this channel, please subscribe to the channel, don't forget to press the bell icon and also like the video, okay. Bye. Elementary operation does not change rank of the matrix. Elementary change, you cannot make a generalized statement like this. Elementary operations, there may be some operations which can change, but it is always true that the rank will be less than or equals to, it cannot exceed. That is one we can surely say. Okay, the best way to check with some example. Chalo, bye bye, take care guys, see you tomorrow at 8 am.